So let's talk about disorders of fluid and electrolytes. Um, so typical disclaimer, this isn't everything that you need to know for the test. Learn what's on the packets. The reason why I'm doing these is hopefully be able to explain a little bit of the reasons why some things are that they are, simply just review some things that are in your packet and help sort of just review the general ideas. So, first let's talk about an electrolyte. What is an electrolyte? So it's an anion or a negative ion or a cation, which is a positive ion. And they're always balanced. So, a positive two plus cation, like calcium, will always be balanced with two um, negative one anions. So they're always in this balance. Um, Talking about diffusion and osmosis, we talked about this a little bit in the last lecture, but diffusion is when the particles are become even um, on two sides of a membrane, and then osmosis is when the water or the fluid wants to be, wants the same ratio between fluid and solutes. So water will move. So diffusion is the particles or the solutes are moving. Osmosis is the fluid is moving. Okay, so reviewing osmolality, specific gravity, and tonicity. All of these are extremely similar. So if something has a high osmotic pressure, it means there's a lot of solutes, it'll pull a lot of fluid. And that's the same thing as tonicity. So tonicity is the ability of a of a solution to pull fluid. So if there's high osmolarity, it'll have a high tonicity, and also the same thing as specific gravity. Specific gravity is the a quantity of solutes. So if you have a high specific gravity, you'll have high tonicity and you'll have high osmolarity. Okay. Um, So there's different spaces where fluid can exist. We have the intracellular space, and then the extracellular fluid is divided up into the interstitial fluid, which is outside the blood vessels, and the plasma, which is in the intravascular space. And there's also the transcellular slash potential slash third space. So let's talk about a little bit about these things. Um, So something that is will help you to understand some things that are in the packet is fat does not contain a lot of fluid. So in obese and older adults, and typically older adults are more obese than younger adults, they'll have less water because they have an increase in fat. And water is typically about 55 to 60% of total body weight. So this fluid is continuously being exchanged between the intravascular space and the plasma and the interstitial space by hydrostatic, which is push pressure, and oncotic, which is pull pressure. So the oncotic pressure is kind of like that osmotic pressure, pulling that fluid. And then um, hydrostatic is push. So um, hydrostatic is like if you are dropping a fluid, it'll kind of spread out. So it's kind of that pushing effect of gravity. And then sodium is the most abundant extracellular electrolyte, and potassium is the most abundant intracellular electrolyte. So um, if cells are being destroyed, you're going to have high potassium in the bloodstream. So if, for example, if you are doing chemotherapy and you destroy a tumor, which has a lot of cells, your potassium in your blood will go way up because there's so much potassium in the cells. So think potassium intracellular, sodium extracellular. Transcellular spaces are things like the eye, synovial fluid in the joints, and cerebral spinal fluid. So it's just something that doesn't really fit in the other categories. And then effusion is water leaking into a potential space. So that can be like ascites. So that's when fluid leaks into the abdomen, which is a potential space. And then generalized body edema is called anasarca. So think anasarca, like a parka. Parka can hold a lot of fluid. So That's generalized body edema. And so, talking about hypertonic and hypotonic solutions and what that does to cells, if you think about it, if you have a cell in a hypertonic solution, meaning there are more solutes in the fluid outside the cell than inside, then that'll cause the cell to shrink due to osmosis. So that fluid is going to seek the fluid with higher solutes, and so the fluid will flow out of the cell into the fluid around it, and the cell will shrink. Isotonic, it'll stay the same, right? Because there's the same amount of uh, 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 osmolarity inside the cell and outside the cell. And then hypotonic will cause the cell to swell because there's more solutes in the cell than outside, and so the water will flow towards the solutes inside the cell, and that cell will swell. Um, so we want to have this body water balance. So water is really important. It's needed to eliminate metabolic waste. And when somebody has a high body temperature, they'll need more water. So higher metabolism, all these things, your body's working more, they will need more water to be able to help with that. So, and then talking about excretion of water in the urine. So the minimum in 24 hours is 400 milliliters. That's like the minimum normal amount. And then oliguria is 400 to 100 milliliters in 24 hours. And think like oligarchy is leadership of a few people. So oligo means few. So it's not nothing, but it's not very much. And then anuria, A is like nothing. So they have less than 100 milliliters of excretion in 24 hours. Okay, sodium. So when you see sodium or abnormalities with sodium, typically you want to think something's wrong with it's going to affect the muscles and then also affect the nerves and just the central nervous system um, in general. So the typical normal range is 135 to 145. Uh, know that you'll need that in all of your classes. So 135 to 145 milliequivalents per liter. And the reason why this affects nerve and muscle fiber transmission, so a little bit of a review of physiology, is um, the inside of a nerve is negatively charged due to that active transport. And so when acetylcholine hits the receptor, it'll open channels which will allow sodium to go into the cell. So sodium is a cation. So when that sodium goes into the cell, it depolarizes and it fires that action potential. So if you don't have sodium to be able to flow into neurons, then you're not going to have as much nerve transmission or muscle transmission because the nerves affect the muscle transmission. So that's why sodium will affect nerves, nervous system, muscle fibers. And then your urine is essentially sodium free. Um, one of the reasons for this is that we do lose salt or sodium through the GI tract and also through sweat. Okay, so different kinds of hyponatremia, so low blood sodium, is hypotonic or dilutional. So this can occur if you're running a lot, you're sweating a lot, and you're losing that sodium in your sweat, and you're drinking pure water. So hypotonic, that water is a hypotonic um, solution. You're not taking in sodium with that water, it's just pure water. And so you're losing the sodium, and then that water is diluting the sodium that you have left. So um, that's why, people will suggest things like Gatorade or other um, electrolytes when you're sweating a lot because it helps you to replace that sodium and other electrolytes. And then hypertonic hyponatremia um, can be from, for example, high glucose. So if there's a lot of um, blood sugar, then that blood sugar will increase the tonicity or the ability to attract fluid, and then that fluid will dilute the sodium in your blood because there's just so much fluid, so much blood sugar. Um, just a basic principle, if you lose a lot of fluid quickly, you'll want to give it quickly. But if you lose it slowly, you'll want to give it slowly. because the body adjusts. And so your body will get used to one thing, and if you lose it slowly and your body adjusts to that, and then you try pumping somebody full of fluid, it can cause a lot of bad effects. Um, and then hypernatremia can result in dehydration because that sodium has that high tonicity, right? So it's pulling water out of the cells, and then you'll have a lot of fluid in your blood vessels going to your kidneys, and uh, you'll pee out fluid. So that can cause sticky mucous membranes, decreased urine output because you're dehydrated, and then decreased blood pressure because you'll have less fluid in your blood vessels, so less pressure. Okay, so potassium, when you see potassium or abnormalities with potassium, think problems with the heart. And one of the reasons for this is the effect that it has on the membrane potential. So you can see it. You don't need to know this, but this can just help you to. I, I don't think this is in your packet, but this can help you understand why potassium has this effect on the heart. Um, Hyperkalemia and hypokalemia can cause it to be easier or harder to depolarize, and that just causes abnormalities with the rhythm. Um, and so when you're giving potassium to somebody, it either needs to be oral, or if you're giving it intravenously, it needs to be diluted. Um, and something that our professors teach us is that's one of the ways that they'll do the death penalty for um, prisoners on death row is they'll just give them a bolus of potassium. It knocks out their heart and then they die. So that's very important. Okay, so um, talk about this hydrogen or proton and potassium balance as well. Talking about potassium, um, there's a lot of potassium in your GI tract. So if you're vomiting or you have diarrhea, those things can cause hypokalemia because it's washing out that potassium. Another important principle is that insulin not only drives glucose into your cell, but it also drives potassium into your cell. And so um, here, we're talking about acidosis and alkalosis. And this is something that um, is so important with the body, understanding what causes the body to be acidotic, what causes it to be alkalotic. So in acidosis, a patient is likely to be hyperkalemic. Why is that? So a proton is essentially acid. So if you have a lot of protons in your blood, your body will create this mechanism to get rid of the protons or make your blood less acidic. So your proton is a cation and your potassium is a cation. So it says, okay, I'll swap this. So it'll bring the protons into the cell and I'll swap it with a potassium because it always needs to be even, right? Always needs to be equal, cations and anions. And so that'll cause you to be hyperkalemic. Um, and then alkalosis will be the opposite. So if you don't have enough protons or enough acid in your blood, it'll take your cells will take your potassium and it'll replace it with protons to make it more acidic. So that's how acidosis and alkalosis can affect um, your potassium in your blood. And this is also important, for example, if you're giving insulin, insulin puts blood sugar back into the cells but it also brings potassium. And so that can cause hypokalemia. And then there's something called pseudo hyperkalemia. And this is essentially an error in a blood draw. Not an error, but it's something that can happen where the blood lyses as you're drawing the blood. And because the blood cells um, have potassium, or blood cells don't have the blood has potassium in it, and when the cells lyse, there's potassium in cells. So there'll be extra potassium that'll show up, even though the blood might have normal amounts of functional potassium. That blood will show as if it had hyperkalemia. Okay, so chloride fluctuates with sodium because sodium chloride typically that anion and cation goes together. Um, so The amount with this is going to be 95 to 105. Also forgot to mention potassium is 3.5 to 5. So chloride, 95 to 105 milliequivalents per liter. So if you have more sodium, that is pretty much going to mean that you're going to have more chloride. Chloride is important to make the stomach acid acidic, and it's also essential in expelling bicarb from the body. So we'll talk about this more later, but bicarb is alkalotic. Um, so if you have low chloride, you're going to have high bicarb, and your body will be in alkalosis. And this can cause you to have, um, well, and this is why hypochloremia causes shallow respirations, because you're trying to not expel that acidic CO2. But if you're hyperkalemic, you'll have that Kussmaul's breathing, which is deep and rapid, which is trying to expel acidic CO2. So low chloride will be alkalotic, high chloride will be acidotic. Okay, calcium. Calcium is controlled by vitamin D. Vitamin D is important for calcium to be able to be metabolized and used. So parathyroid hormone brings um, calcium out of the bones into the bloodstream. And then calcitonin takes calcium and puts it back into the bone. So calcitonin is released by the thyroid gland. It's also important to consider albumin level when you're looking at calcium because calcium binds to albumin, and when it's bound to albumin, it's not functional. And so if you have a super high albumin level and a super high calcium level, maybe that calcium isn't actually like high. It won't be a problem to have that much of it because so much of it is bound to albumin. So take into account how much albumin has when you're measuring calcium. And then pseudo hypocalcemia is the same principle. If you have low albumin, then maybe if you have like low calcium, the active amounts of calcium might be about the same as if you had normal albumin. Also, normal calcium levels help stabilize cell membranes, so they'll depolarize normally. So without normal calcium or in hypocalcemia, more sodium can enter the cell and depolarize. So patho is really in the weeds with this one, but pretty much you'll have increased muscle contraction. So that's what causes the Trousseau sign, which is the arm bending with the blood pressure, and Schwastek, which is the face twitching when you touch the face. That's like it's depolarizing easier um, because of that calcium level. Um, okay, so also prolonged immobilization can cause calcium to leak out of the bones and into the blood, and that causes hypercalcemia. If you're not doing that weight-bearing activity, then your bones will leach that calcium. And then hypercalcemia causes decreased neural excitability. So hypo causes increased neural excitability with all the twitching and stuff. Decreased neural excitability is a result of hypercalcemia. So that can be manifested in stupor, weakness, the flaccidity of the muscles, and things like that. Okay, so briefly, magnesium and phosphorus. Magnesium is essential for potassium absorption. So if somebody has low potassium and low magnesium, you're going to give magnesium first so that the potassium can be absorbed. Um, and then hypo and hypermagnesemia, that manifests similarly to calcium. So no calcium, and you'll know those. And then phosphorus is taken in with protein and it's essential for ATP production.